So, welcome back, everybody, and to this new topic. So, the topic today is still a continuation of what we have been discussed with deep learning. So, last week and the week before, we discussed the recurrent neural networks and neural networks and how also to use them to solve differential equations. Now we are entering into a topic which is very, very interesting, and that deals with models which are tailored to time series, but these models, like recurrent neural networks, are also extremely useful in natural language processing, the analysis of time series. They have served as a prototype, or what we should rather call a first approach in the large language models. So being able to program or to understand what an RNN is actually a very, very interesting thing, in particular if you're interested in these kind of topics. So if time series is something you're dealing with in your research project, a recurrent neural network with its different implementations is one of the more favorite methods. Now, today, we are going mainly to keep lecturing in the first hour. And you probably saw from the mail that we have one of the founders of deep learning, Joshua Benjo, who is giving a seminar from 3 o'clock and on. And there will be the Minister of Research, and also I think the Minister of Infrastructure or something like that. So it's going to be a pretty famous group of people coming. So Joshua Benjo is one of the really leading researchers in deep learning. He's actually one of the co-authors of the textbook which we are using. So I thought we are going to discuss now this for till 3 o'clock. If you want to stay over, don't want to go and listen, I can continue. If not, I would recommend going there. And this is up at the University Library in Auditorium 1. So if people want to hang around here, we will obviously continue with the lecture in the next lecture. Alternatively, we could also discuss the project number 3. Now, concerning project number 3, I wanted to point to some things. So you can find it under the doc folder, but you will also find it if you just scroll down here and look at the end, you will find project 3. We are going to discuss it during the lab session. So the beginning here is the same thing which you've seen as before. We put a tentative deadline of December the 15th. We know that this will, irrespective of day which we pick, will interfere with some exams, but we should have at least 5 weeks for the project. So hopefully this is something which, from a programming point of view, is going to function easier than previous projects, in the sense that here you can use TensorFlow or PyTorch or scikit-learn functionality. And we are going to, if you look at the project, we are going to have several options. So one of the options is essentially that you have your own data, which you want to analyze. And there are groups who already have their own data. And these are things which we can discuss at the lab. We want you to send us an email about the data you want to discuss, so that we can see that this is something which is feasible. Because sometimes using own data can actually lead to quite some problems, because not all the data are streamlined to be read into a given machine learning algorithm. So till now, we have actually taken a very relaxed attitude, in the sense that we've often used data sets which either we generate easily, or we have data sets which have been used with all these different software libraries like scikit-learn, PyTorch, and TensorFlow. And that means that you can just read in the input values and the target values in an easy way. For other data sets, there may be complications in preparing the data. So this is something, when you're using your own data, we have to make sure that you will be able to use them in due time. Because, I mean, it's after all 4 or 5 weeks only. And this course does not have an emphasis on preparing data. Okay? So that's one thing to think of. But we obviously want you to be able to explore things which are related to your research interest or interest in general. But what we want you is obviously that you should pick two of the methods we have been using. So if you think of project 2, which you're dealing with now, we have studied linear regression in project 1, or logistic regression, and you're comparing these results with a neural network. So that is already an example of where you are comparing two different machine learning methods. And often what you will see is that many research papers, they will compare neural networks with, let's say, CNNs, recurrent neural networks, and then you will say that this method seems to fit better for our data set because of this and this. And this is going to be our favorite method in order to analyze this specific data. So just to give you an example, what you could have is some images which change over time. And you want to train a model which is able to recognize what kind of behavior is expressed in these images which change over time. Then you could obviously attempt to do that with a CNN. If you do a standard neural network, this can often become very time consuming because a neural network does not often reduce dimensionality. But then you may have the time element. And then what could be relevant then would be to look at recurrent neural networks, but where at each time step, you have an image recognition mechanism, where you have a CNN. So we are going to demystify the RNNs, the recurrent neural networks, and show you how you can use them in one, training on the solution of a differential equation, and two, training on images which develop over time. So these are typical examples which people may use. Now, some of you may also be interested in natural language processing. And this is something which I don't have an expertise in, but if you are familiar with that topic, this is also an interesting topic for project number 3. So if you're dealing with, say, images, one thing you could do is to start with a neural network code you had in project 2, and then replace the neural network with a convolutional neural network. That would be two methods which you could use to analyze. We are also going to have lectures on another method, which we will discuss next week, which are called autoencoders, which are also very efficient methods in deep learning. So that ends the type of methods which we will cover through this semester. And that is the kind of methodology which we obviously would like you to use when you are setting up project number 3. So when it comes to data sets and things you want to do in connection with project number 3, we obviously encourage all of you to actually discuss with us, just to see that what you're thinking of is feasible within 5 weeks. Any questions so far? Now, there is another path in project number 3. So if you scroll down a little bit, what you will see is that there is a standard differential equation path. And this is the famous diffusion equation. And this is a project which is tailored to those of you who are studying differential equations. So if you're familiar with standard solvers, like a finite difference method or finite element method, this is the project for you if you want to apply the theory you have developed in project number 2. So project number 2 then, with your neural network, is ideal for that project. In that specific case, since you're comparing with the standard differential equation methods like finite element or finite difference, you don't need to add another machine learning method. So this is a project or a path for project number 3, which is more tailored to those of you who may be studying or have studied differential equations. So I may add another one which deals with training a recurrent neural network where you take a differential equation solver and you solve a differential equation as a function of time. And then you train a recurrent neural network on the first few time steps. And then you use the recurrent neural network to make a prediction for the next time steps. This is often done because to solve a differential equation can sometimes be time expensive. So if you rely on your fitting or a recurrent neural network, you can actually train a network on some few time steps in the beginning. You reproduce the results you're training on, and the rest is an extrapolation. This is also a very powerful way of actually handling data from time series, because you can think of your differential equation as a kind of time series. So this is a kind of example which I'm going to use to illustrate to you what recurrent neural networks are. And that is simply because I come from a differential equation world. And that's where I feel familiar. I have never done research on natural language processing, but I can direct you towards the relevant literature. But I don't have what you might call in German, the Fingerspitzgefühl for these kind of things. Okay, so we are going to discuss these things during the exercise, the lab sessions in the coming weeks. I know that quite many of you are pretty stressed with the final deadline, and that probably tomorrow, many people are actually so exhausted after the deadline that you really don't want to start with a new project, but feel free to swing by the lab. Let's go back to the lecture. So what we are going to look at is both the intro and some basic mathematics. So keep in mind that if you would like to write your own recurrent neural network code, this is typically a one-semester project. So we are going to show you how you can run these kind of methods with PyTorch and TensorFlow. And this is typically the kind of approach we recommend in project number 3 if you want to use these methods. This means also that the kind of depth we will dive into when it comes to mathematics is going to be a little bit shallow, okay? So I want to give you more the kind of overarching view, and then we will let those of you who are interested in the implementations, I mean, this is something you can do in more advanced courses. Now, there are some reading recommendations, and many of the slides, which you will see in my slides, actually taken from Rashka's textbook, and in particular from chapter 15 in the textbook. And there's also a nice link to GitHub codes in PyTorch. In my lecture notes, you will find both TensorFlow and PyTorch codes. And the community is a kind of split between using PyTorch and TensorFlow. So if you're more interested in TensorFlow, there are many, many examples, and basically all the authors provide pretty in-depth GitHub repositories with code examples, which you can use. And one of these is actually David Foster's book on generative learning. And there are many, many other textbooks. So if we now look at the background of why we are going to do RNNs, so I'm going to give you a kind of background first, and then we dive into the basic build-up of a recurrent neural network. And then I'm going to, for those of you who are going to stay here, I will obviously discuss how we set up a recurrent neural network. If you prefer to go to Benjo's seminar, I will obviously just put on the recording online after the lecture, the second lecture today. Okay. So if you now look at what we have done from neural networks, neural networks is normally a case where we have a feed-forward step and we have the back propagation step. The data are normally homogeneous. They're obviously often labeled, and we keep the full weight matrix. So normally we deal with what are called affine transformations of the data. The neural networks are, you could actually use them to train on time series, because what you could do then could actually be a kind of sequential thing where the input to the differential equation is used to train the first output, the first time step. Then you take the second time step and you train that one as a new input, and then obtain the results from the second time step. And then you go on like this in a subsequent fashion. This is not very efficient. So when we then move to CNNs, in a typical CNN, the focus has been on images and recognizing images, labeling images, having them labeled, and then try to recognize what this image actually is. So classification type of problems are the one which CNNs have been mostly applied to. But you will also see research on CNNs being applied to regression type of problems. But then when we have sequential data, that is really where these recurrent neural networks have their strength. So if you think of a recurrent neural network, it's actually, as opposed to a regularly fully connected neural network, or just a neural network, that has layers that are connected to themselves. So that means that you have the solution at a specific time, and that feeds in to the next time step, and so on and so on. Why are we dealing with RNNs? So they work very well when you're looking at sequential data, and typically time series is one of the cases. Another property is that they can handle variable input and output. And that's very interesting because at every time step, and this is a kind of example we are going to look at. So at the very end of the lectures, you will find an example which we will probably discuss at the end of the second lecture and also in the beginning of the next one, where we have a differential equation where you have a block which is oscillating back and forth with damping, but then under the influence of an external force. So that means that every time step, there is a force which acts on your system with different strength. So that means that the networks are flexible in the sense that you can have different inputs to the system at different time steps. And this essentially, if you're having an object which is oscillating back and forth, or if you're looking at how a patient behaves under the influence of some kind of measurement over time. So if you're looking at cardiac disease, you may be interested in studying the blood pressure of a patient. And then you can just measure the blood pressure as a function of time and see if there are irregularities. And then train a model to the blood pressure of that specific patient. So that's a typical example of a time series which you could use. Or you can have sound files, which is another typical example. So they're very flexible to the type of input and output, which you may need as you move on with time. So the network would not know. So if you think of if you have trained a regular feed forward on the data set with 2 features, it makes no sense to suddenly add a 3rd feature. So that's typically a problem with a standard neural network. Now, one of the things is that these recurrent neural network can actually vary in structure, in architectures quite a lot. So the simplest one is just to have a simple neural network for every time step which you train. But you can have convolutional neural networks at each time steps, and you can have more complicated learning processes at every time step or every step. So I'm so used to use time because I work often with time series or time evolution of physical systems that I tend normally to say time, but it doesn't need to be time. If you go to natural language processing, you will not use time as a variable. Now, one of the problems is that you end up often with vanishing or exploding gradients. And this is something which we are coming back to when we look at the mathematical details of a recurrent neural network. So it looks very much like a standard feed-forward neural network, except that it also has connections which are pointing backward. So they often, as I said, used to analyze time series. So if you're interested in analyzing stock prices, we actually had once, some 2-3 years ago, we had a participant of this course which was doing a PhD actually in economy, and was analyzing stock market prices and how they varied over time from a specific, I think it was the Sao Paulo stock market. This guy was from Brazil, by the way. That's why this person had this kind of data. So these are also possible data sets you could look at in the 3rd project if you want to study recurrent neural networks. So I just wanted to start a little bit with a simple example to give you a teaser on the basic philosophy. So the example which we have here is a simple recurrent neural network, and this is done with TensorFlow. So we are going to discuss the simple RNN today. and look at the examples and how we can encode it. And in this case, I'm actually setting up a very simple data set. So my X values are given by, or my data set is now given by a sine function, which is a function of time. So I'm going to have 1,000 time steps, and I'm going to train it on the 800 first time steps. That means that the 200 next ones are going to be a prediction. So I will be training a recurrent neural network to fit the first 800 time steps. And in the beginning, I'm just going to take away the randomness. And let's just run this one and see what happens. So we're coming back to the technicalities later, but I wanted to show you some of the things which we can do. And then you will see that in this specific case, we have 32 nodes in a hidden layer. And then we are doing this for many, many time steps. But what this example is doing now is that all the parameters are set to be the same for all time steps. And you will see that this is a typical approach which is used, because else, if you're having weight parameters at every time step which differ, this is going to require a lot of memory and a lot of training. So it's pretty common to often, when you do the training, to keep different parameters for some few time steps, and then use these parameters for the remaining time steps. In this specific case, we are actually using the same parameters. And you see that in this case, we have something like 1,184 parameters. And then we have a new layer at the end here. And you will see here that when we are doing the training and look at the final figure, so it takes some time. So the blue line is actually my original one. And you see now that this is going up to time step 800. So I'm fitting a sine function with a recurrent neural network up to the first 800 time steps. And that means that what comes here after 800 to 1,000 is a prediction. So that means that I have trained a network on this data to make a prediction after some time step. So as I mentioned at the end of the slides here for this week, and we will probably discuss that next week, there is an example where you solve a differential equation, and then we take the first time steps to fit a recurrent neural network, and then we use these parameters or the fitted network to make a predictions beyond the data sets where we have done the training. So I wanted just to bring in this example to give you a kind of overarching view of how we would be using many of these network models. Any questions? Does that sound reasonable? So this is a kind of overarching view we're going to take on it. So let's now, before we go into more details, let's just look at the basic structure of a feed-forward neural network. So I'm going to jump back to the whiteboard and then look at some of the basic elements which we are going to deal with. And what I'm going to do is to use a standard differential equation as an input example to the structure of recurrent neural network, so that you can see the link between a physical case and the networks themselves. So what I'm going to take now is an equation which many of you probably have seen many, many times. So let's just do that. So intro to RNNs. And we are going to use a differential equation solver, which many of you have met before. And this is just Newton's equation of motion for a block which is oscillating back and forth. It has friction, and then there is an external force which is applied to the system. So you have the acceleration term, and we're just looking at this in one dimension as a function of time. So this is the standard acceleration which we have in Newton's law. I hope you don't get offended if I bring back equations like this. Then we have some damping term of the motion. We have a d of x. So this is the same as a velocity dependent term. So you can think of this as some kind of damping or friction. well, let's just call this damping. Then, since this is an oscillatory motion, we have an x, which is the unknown quantity, and then we have f of t, which you can think of as an external force. So what I'm going to do is actually to use this one and portray it graphically. And then when you have the graphical image of how you solve this differential equation, then we are going to bring in the concept of a simple recurrent neural network. And then you will see how the different elements come in when we generalize the equation here, which we're going to translate into a graph. And then that graph is going to serve as a way to visualize what a recurrent neural network is doing. So let's look at the equations which we have. We know that v is actually dx dt. So that's a differential equation for the velocity. And the typical way we solve a second order differential equation, and as I said, I hope you don't get offended if I remind you of this, is actually to rewrite it as two coupled first order differential equations. So that means that you would take this equation here and plug v into here, and obviously here, and that means that you would get another differential equation where you would have m times dv, this is the acceleration, because that's just the second derivative of x with respect to time, plus this parameter eta, which can be some experimental parameter. And now I'm skipping the t dependence, so you have x, and this is equal to f. Now, what you would typically have in order to solve these equations are some initial conditions, which we typically label as a x0. So t0 is the initial time, and a v of t0, which we typically label as a v0. And the way we solve this equation is then to discretize. If we also divide by m here, if we divide here by m, then we can isolate dv dt. So we get two differential equations where we have v is equal to dx dt, and then we have dv dt, which is the other equation, which is now simply, when we now shuffle over to the right-hand side, m times v minus x divided by m plus this force f divided by m. So the example which you will find at the end of the lectures for this week and partly next week is actually this example here. So that's why I'm also bringing it up, because you will encounter it again. And then you would typically discretize. This is the way you solve the differential equations. And then you can call your best possible differential equation solver and use that one to generate solutions at different times. So you would typically let v go over to v of I, exactly as we did when we discussed the solution of differential equations with neural networks. And then we would have a v of t of I. So the data which you could generate in, say, project number 3, if you want to do something like this, could be you having a differential equation solver, which then generates the input data for you, and then use a recurrent neural network to train on the data you have from the differential equation solver, and then make predictions based on that. So we would have some x of t of I, so this is a given time step. This t of I, and this is something which we discussed also in connection with differential equation, is given by t0, the initial time, times a time step, delta t, multiplied with I. Then I typically takes values from 0, 1, 2, up to some final point, n. And then we have that this delta t is given by tn, the final time, minus the initial time, divided by the number of points. So that's a typical formula you will encounter. And if you then think of Euler's method, there is a simple way by which you can set up the update of the points. So let's just set up Euler's method, which is the simplest possible numerical method which we can think of for solving this differential equation. So in that specific case, what we would have is an update of x I plus 1. The next time step, x of I plus a delta t multiplied with the derivative, which is v of I. Then if we look at velocity, we would have a v of I plus 1, which is equal to v of I plus a delta t multiplied with a derivative, which in this case is fy minus eta times v of I minus x of I. So this is essentially the type of equation. So what we're going to do now is just look at velocity. So we don't care about the position. So this is more than sufficient to make the link between a differential equation and its time evolution and a recurrent neural network. So let's now only look at V. Look at V only, and that is more than enough. We can fit X as well if we want to. There is nothing which hinders you from doing that. So the way you could think of this now is that we replace the equation you saw previously, and just replace it with a function f, which we know depends on x of I, it depends on v of I, it depends on delta t, and it depends also on this force f of I. So what we have done now is just to take this equation which we have here and just generalize it into something like that. So how would this look like when we now are setting up the equations graphically? So let's just make a graphical representation. So if you look at that, you could now think of u starting with v0. This feeds into this function f0, which also receives an external probe, f0 and x0. Then this produces a new value, v1, which then is fed into the next function, f1, which also receives f1, x1, and this obviously produces now a v2. So if you just look at the structures of the equations here, you see that v of I plus 1 depends on x of I, v of I, delta t and f of I. So v of I feeds into that one. The only thing I've done now is just to put a subscript here. So I could have actually written a subscript here, f of I. And this continues all the way to the final velocity, which is the velocity at the final time. So we will then have, if this just continues, this feeds into an f of n. Well, actually it's an f of n minus 1. And then we have f n minus 1, x n minus 1. And this produces the final velocity at the v of n. So this will be a graphical representation of this equation. Now we are going to do one more intermediate step towards a recurrent neural network. So let's try to do that. So if everybody has this type of simplified equation, what we could do now is to assume that at every time step, we make a measurement, a real physical measurement of the velocity. Okay? This is a way by which we now could compare our differential equation solver with real life. So let's look at this in a more general term. And suppose now that we down here, we have V0, which feeds into this function F0. So I try to write functions as boxes, F0. And then, so here we're just looking at a differential equation solver and X0. Now this produces an output, V1, which is also fed into the next function, F1. This receives an input, F1, X1, and this just continues with a new velocity, V2, etc., etc. And now you could think that this V1 is fed into some kind of cost function. So we could now have an L1, a loss cost or loss function, and then we have a V1 observation here. And then we would repeat the same thing here. We get a V2 here, which is at every time step, it's actually being fed into a given cost function, and where we have an observation. And this goes on till the final time step. Goes on to V of n. Now, in this particular case, we are just taking the observations and we're just comparing them with our model. So our model here is the solver for the differential equation. Then what you could compute at every time step is a difference between an observed value and what your model is doing. But we're not doing anything else with it. So this could just be you calculating the difference, the absolute value between the two quantities, the observation and your model. And then you would, at every time step, you would just tabulate this difference. Then what you could do is to accumulate all the differences and divide by the number of measurements, and then find a global error for your model. So that would be a typical situation where you could now compare your model with your favorite differential equation solver with what you observe experimentally. Okay, does that sound okay? So this is just one way of thinking of it. And what you will often see is that this kind of graph is often written in a more compact way, like this. So you would have a V0, which feeds in to this function f. It feeds out a V of n, the final value. And then in between, there is a set of operations here. So what you would say then is that this represents different operations. Okay, so now we have a graphical image. What we're going to do next now, since I said that these L functions, which we have at every time step, now could represent us just computing the difference between the architecture of the model, which we have, and an observation, we could now think of, instead of having, let's say, a fixed numerical algorithm, we could replace this f with a neural network. Then the L's would be the cost functions, which we would try to optimize at every time step. You see the difference between this, the first thing we did? So you could think of now the functions f being replaced by some kind of neural network. And that neural network produces an output at every time step. And that is fed into a cost function, which then compares it with observations. And then you try to find a way to optimize the parameters of your model. So when you have a differential equation solvers, things are fixed. You have a Runge-Kutta method, or you have Euler's method, and that is just fixed by you. So there are no parameters to tune while you're running the calculation. Now you can think of tuning parameters for every time step in order to find the best possible way to reproduce your data. So let's look at how this could look like if we now want to move one step further. So let's take back the kind of same way of thinking. And what I'm going to do now is just to make some small changes. I'm going to let this function, which I call f, be replaced by a new function. So if we now write the model which we put up, f of I plus 1 equal to v of I, and I'm going to skip this f of I, the uppercase letter f. So we had this, a function which depends on x of I, and then I had my dependence on actually v of I, but now I'm going to let this be something which may depend on, on v of I minus 1. We had f of I, and we had delta t. I'm going to simplify this one into a function h, which now depends on only x of I, so I'm going to skip this f. So this quantity here, something I'm going to leave out. I'm going to leave out this one. I'm just going to make some simplifications. And this will now depend on v of I, which is a function of h of I minus 1. And I'm going to call this for h of I. So what I'm going to say then is that v of I plus 1 is equal to this h of I, and v of I is equal to h of I minus 1. Then I'm going to define a new cost function, L, as a function of parameter theta, which is now the sum from I equal 1 up to the final step, which is just the sum of all these individual cost functions. And this is going to depend on theta, the parameters, an output y of I, and an output, a target value t of I. And I'm going to let v of I be represented by y of I. So I now want to make it more general. And I'm going to skip the specific relation to velocity. And I'm just going to replace velocity with y of I. And this t of I is now not going to be time, but it's going to be the target value. This is the value we want to reproduce. So what I'm going to set up now is a network which is going to look like as follows. It mimics what we did here, but now we are going to have functions with trainable parameters here. So if this was my favorite differential equation solver, then everything is fixed by the parameters of the differential equation solver if you're dealing with a Runge-Kutta to, let's say, 4-4. So let's now write this down as a network. So I'm going to have an input value, h0, which then feeds into some h1. There is some external value, xi, which is fed in at every single time step. Now this one feeds into an output. So this is y of I, y of 1, sorry. And this goes into my cost function at that specific step, which I call L1. And then there is a target value, which I call T1, which then feeds in here. So what I obviously want now is to make a model where Y1 is going to reproduce T1. So Y1 here is the output of this specific model. Now what I'm going to do as well is to have trainable parameters. So this can be H1 and H0, etc., can be a neural network. So there's going to be parameters here, which I'm going to write with a W, and I'm going to write this as an HH to indicate that there are parameters which connect these two guys. But then there are trainable parameters which connect the input with this intermediate step. So the parameters now are going to be called WH of X. Then there is a new set of parameters which connects H with Y. So you see now quickly that if we are thinking of this H1 as a neural network, that is getting input from a previous step. It has a connection with the outer world, with X1, and it produces an output. So if you think of H1 here as a neural network, the way you could think of this is that it receives some data, and then you're training weights here. You're training weights here, exactly as you did with a neural network previously, where this could be the input to the neural network and links the input with the first hidden layer. This guy here could contain many hidden layers if you want to. Then there is a transition from what you've been training here till the output. And if you're dealing with a regression case, there could just be one output. So that could be a so-called linear function, which is being used here. And then you would have weights which link the internal nodes with the output nodes. Does that sound reasonable? So you can think of this as a specific neural network with a given depth, and where you feed in an input which depends on your time step. And then at every time, it produces an output. So this could be your input position, the output velocity, which is then compared with an observed velocity. Then we would just continue along this line. So we would have a new node here, where we now have an H2. We have a new input, X2 here. It produces a new output, Y2. And it has a new cost function, L2, and a new target value, T2, to which it compares its results. And this continues all the way till the final H of n. And we have an output, an input here, X of n. This produces a final output, Y of n. And then we have a hidden layer, no, it's not a hidden layer, but a cost function, L of n. And then we have the target value, T of n. And in every case here, we have weights, HY, we have WHX and WHH, and that continues. So you could train different weights and biases as well for every time step, but this becomes quickly time-consuming and also extremely memory intensive, because you would have to store all these parameters as a function of time. And if you're having many nodes, this quickly becomes very large. You see the transition from the simple differential equation, where we now, instead of training a function, L, here we could just make an observation of the difference and collect the differences and divide by the number of observations. Alternatively, we now replace the differential equation solver with a neural network, which is going to train on the data which we have. And this data could just be experimental data. So it could be you having observed the velocity of a car at different time steps. And the only thing you want to do with a recurrent neural network is to find a model which reproduces the observations. Alternatively, you can do, as I said, you can train some model with a differential equation solver and use that as training data for a neural network, assuming then that the differential equation solver gives you the correct results. So you can actually use many, many different types of data sets. You could replace this kind of data with images which are time dependent. And that means that in every time step, you would have a CNN, which is doing the image classification for you. Does that sound? I'm just trying to give you the overarching view. And after the break, we're going to look at how we train it and some of the bottlenecks which we quickly can face, because we can easily end up in a situation with exploding gradients. And you will see why we can get exploding gradients or vanishing gradients. So that is a typical training problem with a recurrent neural network. So I'm going to try to stay at this kind of more overarching way, take this overarching view on the system. And the kind of mathematical detail we are going to give you is a little bit more shallow, so that you see how the networks are being trained. But we will not go into those details where we need to write our own code. I hope that's okay, and you don't get offended if we don't bring in more details. The important thing now is to have the kind of overarching view on what we are going to do. So I went a little bit over time. I'm going to stop the recording here. So the thing which we want to do now is to look a little bit at the type of training which we typically do with recurrent neural networks. And then we're also going to look at some of the problems which typically appear in the training of recurrent neural networks. So let's go through some of the details here. So if you look at what we have, the final cost function in this particular case, when we look at what we have here, is going to be a function as we put up before the break, which is now going to depend on the output variables at every step, the target values. So T now is no longer time, but it's a target value which we want to reproduce, and then all the parameters. So this network, the way we train it, is in principle not so different from the way we train a standard feed-forward neural network. There's going to be a feed-forward pass, and then we are going to have a back propagation pass. But this time, it's called back propagation in time, by obvious reasons. So the chain rule, the way we saw it in Project 2 and in connection with neural networks, the basic principles there are the same which enter the training of a recurrent neural network. So as I said some time ago, if you have understood a standard feed-forward neural network, you have many of the basic elements for the more advanced methods like a recurrent neural network or a CNN. So what we have here would be something which then will depend on specific parameters. So we're going to have a given activation function. So this variable h of I, which we wrote, is now going to be given by some input values where we have a activation function. So this function here, sigma, is just one of the standard activation functions. It can be a ReLU, it can be a sigmoid function, a tanh, or one of the favorite ones. So this is an activation function. And if we look at this variable z here, this is going to be given by the weights which connect with the input x of I at a given time step. It's going to connect with the variables from the previous hidden layer. So that contains all the information. So we're actually feeding in to the new hidden layer the results from the previous hidden layer. So this is multiplied with h of I minus 1, and then we will have a bias, b of I. So this plays the same role as a bias. So if you look at the figure which we have, this is one of the types of inputs, and that means that the trainable parameters which we need to look at is these ones, and these ones. So these are trainable parameters. Like this. So let's take a look back again at what we have. So this variable h of I, which we have here, receives an input from the previous layer, and it receives an input here. Then, if you think of this as your output of the network, then there is an output layer, and that has its corresponding weights and biases. So it means that this variable which we put up, this y of I, is then going to be given by a new activation function, so which we're going to label as a sigma y, and that takes as input this variable r of I, and this r of I is now simply going to be given by w h of y, the new weights, multiplied with h of I plus a c of I, where this is also a new bias. So this becomes a trainable parameter. So these are the trainable parameters. This one here is a new bias parameter. So that means that if we look at this, we have 5 sets of parameters to be trained. We have the weights which link the input with the hidden layer, the weights which link the previous hidden layer with the new hidden layer, a bias, the weights which links the hidden layer with, at that specific time step, with the output, and finally a standard bias. Plus that the architecture then, if you look back at what we have here, this could be a deep network, or it can be just a shallow one. So clearly, the deeper you make it at every time steps, the more training you need to do and the more resources you need, by obvious reasons. So how do we actually typically train this kind of networks? So one thing is that we have a set of parameters which we need to train. And now I'm labeling this in a generic way because these could change from time step to time step. So a very brute force approach would simply be to have lots of trainable parameters at every time step. Now, what is normally done is that we have something which is called weight sharing. And that means that we have a truncation of number of steps where different weights are trained. Because else, this will require a lot of memory and a lot of cycles in order to train a network. But in a general way, the type of parameters which we end up with are parameters of this type, WH of X, the parameters B, the biases, and C. So these is a common container for all the parameters. Now, when we are dealing with this type of methods, what we typically often do is something which is called weight sharing. So weight sharing means simply that we truncate, so that is a truncation of number of steps where different weights are trained. So you could think of, if you have, let's say, 100 time steps, you could then have a varying training for the first 10 time steps. And then when you reach time step 10, you keep the same weights for the rest of the network. Because this can quickly, as you can see, grow in dimensionality. So the image which you see here is pretty simple when you look at it, but it can be heavy to train. So one thing which is often done also, since this type of network, which you see here, is difficult to parallelize because it's extremely sequential. So this result here depends on this one. So you have to compute this first, then this one, then that one, etc. Is often to take away this link and simply let this value be put in to that network so that there is no connection between these ones. And then you can train separately the different time steps. So this standard, when you look at the simple RNN in TensorFlow as a functionality there, it means that we are setting up something which looks like this. So next week, when we go into the more programming details and how you can set it up, we are then going to go back to this image here and see how this is implemented numerically. So weight sharing is one of the typical approximations which is done. And the training, when you look at it, is normally done iteratively. Training is done iteratively. So you would have a feed-forward pass. You would then initialize weights, etc., and biases, as you did with a standard neural network. And then you have the next step, which is the backpropagation in time. And the backpropagation in time means that we need to evaluate gradients of 5 quantities. So we will need the gradients of all these guys. So we will need a delta L, where L is now so this has its parameter, this has its own, same with that one, same with this one, and same with that one. So we will need to calculate the gradients using the chain rule of all these different quantities. So this clearly complicates the standard feed-forward and backpropagation, which we have seen previously. But in principle, it's again the usage of the chain rule which comes into play. Now, one of the problems which this type of method actually can exhibit is the problem of exploding gradients. And there's a simple way to understand that. So let's look at that before we go back to the Jupyter notebook. So let's look at the problem. So it's both exploding and vanishing gradients. Exploding and vanishing gradients. So we're going to make some simplifications in order to see this. And let's do that. So if you think of the gradients, so suppose we only focus on one of these parameters. And what we're going to do now is just to make a simpler case. So focus on, and this is actually the parameter which can blow up on HH. So that is the weights which link the different hidden layers from different time steps. Because this is the one which is going to be propagated. If you look at the network here, this is the parameter which will propagate throughout the network. The other ones are local guys here, which live here and here and here. So when we now look at only that one, this will involve derivatives of the following type. So it involves derivatives of the type, if we now look at the d of h here, d of h of I, and then it will have derivatives with respect to a previous layer at a previous time. So these are typical derivatives which we will include. And if we set up this in terms of the chain rule, we could now think of starting at k plus 1 of n here, and this would typically be a dh of I with respect to previous layers starting at the endpoint. So this is actually, which is a part, I should say that, which is part of dh of I with respect to this weights HH. Now let's make now a assumption, and we assume that we are sharing the weights between all the time steps. As if we do that, then we can make an analysis here which actually shows how the gradients can explode. Assume weight sharing. And when we do the weight sharing, what we're going to say now is that this WHH is just equal to a weight matrix W. We're also going to make another assumption. So when we've done this, what we don't know then is that H of I is actually equal to W times H of I minus 1. So H of I minus 1 is the output from the previous time step and the hidden layer. So we are connecting hidden layer to hidden layers. So that means that the hidden layers are those which are going to take care of the previous information and link that with the new information. Okay, so if you look at this function here, so we have H of I equal to W times H of I minus 1. That means that this must be equal to W times H of I minus 2. And then we can continue like this and simply do this T times, and this brings us back to H0. So since the weight matrix is the same, right? We are assuming weight sharing. So this is just to simplify and illustrate what can go wrong when we have exploding gradients or vanishing gradients. So if we make that assumption, what we can assume then is that we then assume that we can diagonalize that matrix. Assume W can be diagonalized. Diagonalized. So that means that what we have then is that if I take W and multiply that with an eigenvector, this is given by an eigenvalue times Wi. And we also made an assumption that this W is a matrix, is a square matrix, which has a specific dimension. So we could assume that it has dimension m times n. Now, if I have that, then what I could assume is the following. I could now assume that this H0 can be expanded in this basis of orthogonal eigenvectors of the matrix W. So I could now assume that there is a sum from j equal 1 up to this n, so j0 and minus 1, of some alpha j, a coefficient of expansion, multiplied with these eigenvectors. So these eigenvectors, they make up a complete basis. Okay, so if I have that, then you will see that if I act with W on H0, that is the same as taking the sum over alpha j of W times Wj, and that is equal to the eigenvalues of alpha j, lambda j, the eigenvalue, multiplied with the eigenvector. If I repeat this t times, do this t times, so what I'm doing then is simply to take Wt times H0 is equal to H at the time t, and that is nothing but us performing this t times. So we have a lambda jt of alpha j of Wj. Now, there's a problem now. So we can obviously sort these eigenvalues so that lambda 0 is larger than lambda 1, of lambda 2, etc. And finally, to the eigenvalue of lambda n, minus 1, since we summed up to minus 1 here. Then we see now that if this lambda 0 is the dominating one, then what we have is that in the limit of t goes to infinity, then we will find that h of t is approaching a term which will be dominated by lambda t0, because that is larger, or often much larger than the other ones. So this will be the dominating term in that expansion. And then you see that if lambda 0 is larger than 1, then the W's acting on the H's can explode. If that explodes, it means that we can risk of getting exploding gradients. So what we are doing here now, if you look at this operation here, is that there's one specific component which is going to dominate when we now propagate back in a network. So when we look at the network here, we are just propagating back here in time, and we do this t times. And that means that when we do that, there may be, if this lambda 0 is larger than 1, there may be a term which will actually can become very large. So in this case, if we have lambda 0 larger than 1, then this term can diverge. Then the h of t term, which is now equal to Wt times H0, can diverge or become very large. And we risk to get into, and we risk having exploding gradients. On the other hand, if we have a lambda 0 less than 1, we can risk having vanishing gradients. So these are typical problems which are actually pertinent to the training of recurrent neural networks. And if you have the case of exploding gradients, one of the standard tricks, which is normally implemented, is that if the gradient grows beyond a certain value, you just set it back to a smaller value. So one of the standard recipes for exploding gradients is as follows. So this is called gradient clipping. So this is for exploding gradients. In that case, what you would have, if you now have defined G as the gradient, we would simply have a loop here if the absolute value of the gradient, and I say the norm 2 here, is less than some epsilon. This can be a fixed number by you. Then what you would have, if that is the case, then you will simply set G back to a smaller value, which is epsilon divided by the norm 2 of the gradient and G. And this is your end if here. So you start with an if here and you have an end if here. That is a simple trick by which you can then flip the gradients and actually set it back to a smaller value and avoid exploding gradients. But what you see is that when it comes to the training of a recurrent neural network, this is normally one of the risks which you often face, the risk of exploding gradients. So this is a kind of very, very shallow mathematics, which I promised to you. We are now going to go back to the Jupyter notebook, and I want to visualize some of the things we have been discussing, and also how this connects with actual implementations. And at the end, we will start looking at some codes. And then next week, we will show some full case examples, which is the case which we have at the end of the lecture notes this week. Okay, so let me bring back the Jupyter notebook. Any questions so far? Okay, so let's bring back the Jupyter notebook. Yeah, there's a corresponding example. You will find corresponding examples in PyTorch. And as we said now, if we want to repeat, there are some problems with these RNNs. They are very powerful because they typically combine two properties. I'm just going to repeat. They have distributed hidden states that allows them to store a lot of information about the past efficiently. There's a nonlinear dynamics that allows them to update their hidden state in a complicated way. So these are some of the two benefits. And with enough neurons and time, they can actually compute anything that can be computed by your computer. That's a pretty strong statement. Normally, we don't have enough time, and we don't have at the disposal an infinite amount of compute time. So one of the problems is that they can oscillate. They can settle to specific points. They can sometimes behave chaotically. And they also could potentially learn to implement lots of small programs that each capture nugget and knowledge and run it in parallel. And that interacts to produce very complicated effects. But the extensive computational needs of RNNs make them very hard to train. And you saw that from the example in the previous lecture, that when you set up recurrent neural networks, you have lots of weights and biases to train at every single time step. So let's just quickly remind ourselves a little bit of the differences. So these are pictures which I've taken from Rashka's textbook. And if you want to dive into a little bit more of the details, I recommend both chapter 10 of Goodfellow and Benjo and Rashka textbook chapter number 15. So the way we have trained a neural network is like the image you see here. So we have some input, we have some hidden layers, and then we have some output. In our case, we have an input at a given time. We have a connection between the different hidden layers at different times, and that produces an output at a given time. And this is just repeated for a series of time steps. So that's the basic difference when you now look at the recurrent neural network. So what you have here is basically a repeat of what we discussed before the break. So I won't repeat it. But if you now write it out, you can now think of the structure of like this. So you have a set of hidden layers. This could just be a shallow neural network with one hidden layer, which then produces an output which is fed in here. It produces a new output which goes to the next time step, and we have trainable parameters which link the two hidden layers at different times. So the whole idea is that this should be able to capture complicated dynamics between different time steps. So your differential equation solver, in a certain sense, tries to do that, but often a differential equation solver is a linear function. So the strength of RNNs, which is also the strength of deep learning in general, as you have seen in project number 2, when you fit the Runge function, compared with what you did with a standard linear regression, is that the neural network is able to capture complications and or complicated nonlinearities, which a standard polynomial fit was not able to capture. So this is a typical layout, and you can, when you look at this in more detail, you can, if you want to, you can have many more layers here. And clearly, the more layers you have, the more training you need. But it's not uncommon that you would start with one hidden layer, and then you could have two hidden layers, and then you would have a connection between the different hidden layers at different time steps. So what you could think of when you now look at this is that typically the hidden unit actually receives two inputs, one from the output value here, or the input value, and one which comes from the previous layer. So this connects with this one, and this one connects in here. So that's two types of inputs. And then we have different types of modeling when you do this in sequential order. So you could have one final output, and then you would have what we normally call many to one. This is a situation which is pretty normal. Many to many is the one which I have been illustrating with a differential equation, where at every time step, if you look at the figure down to the left, at the bottom left, the many to many is the one which I have been discussing, where at every time step, you have an output which you would compare with some target value. Alternatively, you can have many to many, which differs, where you have some output at some specific steps. So you see now that a recurrent neural network is actually very flexible in the way you design your data. So you could have just data at the end. That could be a final value. And then you have lots of inputs at different time steps, and they conspire to give you a final value like the one you see up here. So the way you design these networks is actually something which gives you a lot of flexibility. You can have just one type of input here. You can have different observations. So the kind of input doesn't change. There is no new feedback into the system at the next time steps, but you just have a general input, but then you have different observations here. So that will be one to many. And the case which we saw is the one which I call many to many. So there's a lot of flexibility in the way you design your input and output data. If you now look at just to remind you, the weight matrices which we have. So typically now you would have to train this H of X here, Y of H. You would have to train this H of H, and so forth. And if you're now looking at these in a single layer, this is roughly what we put up on the whiteboard. So you have some input variables, Z of H here, which is then fed into some activation function, which is this one, and that produces the output, which is then fed into the output layer and is also fed into the next hidden layer at the next time step. And this is basically just a repeat of all the mathematical observables or variables which we need to deal with when we have such a network here. So the next step when we are doing the calculations is actually to do the back propagation through time. So the forward pass builds up a stack of the activities of all the units at each time step. The backward pass, that peels activities off the stack to compute the error derivatives at each time step. And after the backward pass, we add together the derivatives at all the different times for each weight. And the backward pass is actually linear, as you had in a neural network when it comes to the derivatives. And then we discussed this problem of exploding and vanishing gradients. So and these are actually things which we discussed previously here on the whiteboard, so I'm not going to repeat them. So if you look at the backpropagation through time, what you typically need to set up if you want to write your own code is then the result at each time step, which is now typically your loss function. This could be the mean squared error of this time step. And then your total mean squared error is actually the accumulated mean squared error from all the different time steps. So the overall loss can typically be computed as a sum over all the steps. And in the slides here, you will find links to some of the first papers which actually presented the backpropagation through time algorithm. So if you want to look at the algorithm here, what you would typically have is, if you look at these derivatives, you need to calculate the derivatives at a given time step with respect to the weights. And this is essentially you applying the chain rule, nothing but that. So if you look at this equation here, in this particular case, this would then be the derivatives with respect to the outputs, which then these outputs depends on h of t, and then this h of t obviously are then calculated through the chain rule, where you go through all the different time steps. So it's actually pretty similar to what you have done with the backpropagation in a neural network, except that now we need all these parameters for all the different given time steps. Does that make sense? So this is just the first simple implementation, unless, and as I said, it's pretty common to actually set up these WHH to be shared among all the different time steps. And then if you now look at this one, this is actually this quantity which you see here is the one which we discussed when we looked at exploding gradients. This is normally computed as a multiplication of adjacent time steps. And that means that you would simply compute that one as a product over all these different time steps. And that's the quantity which we looked at when we discussed the problem of exploding gradients. And then if we now continue, what we need to set up when we have this, because this is actually one of the problems with both exploding and vanishing gradients. And when you now set everything up, it's actually just a simple implementation of the chain rule, where you look at all these derivatives. You have to have the gradients of the different loss functions with respect to the bias C, respect to the bias B, and then we have these different ways. Actually here, I called V for the one which connects the input X, W for the one which connects the hidden layers. So I actually changed a little bit the notation from Rashka's figures. And then V is the one which connects the output layer with the hidden layers. So the typical RNN, if you want to do a summary, is that you have these weight matrices that connect the input layer, the stage T, with a hidden layer, the previous hidden layer with h of t, and the hidden layer connecting with the output layer at the same stage and produces an output. And the output from the hidden layer is often modulated by a tan h function, that is pretty common, and a bias value. And the output from the hidden layer produces typically a function like this, is produced for a function like this one, where C is a new bias parameter. And the output from the training at a given stage is in turn compared with the observations through a chosen cost function. And this, in a way, is a kind of, how to say, the standard simple RNN in a nutshell. For those of you who are interested, if you want to see more about the mathematics of an RNN and how to build own code on that, there is a link to an example which we developed for another course on advanced machine learning, where this was a semester project. So in that specific example, if you look at this link which we have here, you can actually look up the details more in depth on how you can train yourself an RNN. Now, in this course, what suffices is to have an understanding of what they are doing. And then when you have that type of understanding, we are going to use either PyTorch and TensorFlow as ways to implement the training of a set of a data set. So one of the things which we will discuss next time, which I actually want to postpone because that's a new topic, is something which is called long short-term memory. Because these networks, when you look at them now, they depend on the input from the previous layer, and then the next one, and next one, next one. And this can be computationally very, very expensive. And at the same time, there may be problems with long memory correlations. So there is a way to overcome that. And this is also one of the standard ways which is implemented in many of these natural language processing algorithms. And we will look at this next week during the first lecture. And then in the second lecture, we are going to jump into autoencoders. So I'm going to stop a little bit earlier because I want to rather start next week with the long short-term memory. And then at the end, we're also going to look at coding examples on how we can use a data set from solving a differential equation as an input to a recurrent neural network, and then use the recurrent neural network to train on those data sets. And then when you have a trained recurrent neural network, to make a prediction on times which were not included in the training. So that means that if you sometimes have a very computationally expensive differential equation solver, it's not uncommon to take the first few integration steps and use that as a training model for recurrent neural network, and then extrapolate for times beyond that. Because then hopefully the network is cheaper to use than you implementing your favorite differential equation solver for all time steps. And this is something which we're going to play a little bit with next week. But I hope you see the wood for the trees and the basic structure of a recurrent neural network. And then next week we will practice a little bit and I will show you more code examples than what we did today. But I wanted to go through the basics of an RNN first. Okay, so I'm going to stop here a little bit earlier today.